Well met 216ers, this is Professor Kaufman, and what ensues is an overview of Project 2 for our Fall 25 semester. This is the traditional project structure that we've used in the past, which comprises 3 problems. There is a relatively short coding exercise that has you implement a practical application of some of those bit-level operations that you've used that affects something sort of like an embedded system. We'll have a look at that first. Next, there's a debugging exercise that has you making use of GDB to pass certain phases that are in a provided program. The input to those phases is a little obscure, and the debugger is then essential to figure out what needs to go in order to get you more points. And then finally, there is a data structures implementation. You'll be implementing a very simple binary search tree and a little main application that allows adding things into it, loading it from file, and so forth. Now, because of the fact there are 3 separate problems, and you can take them in any order that you want. I suggest going in order. That's usually what folks do. But the fact there are 3 separate ones that each have their own sort of nooks and crannies and flavor to them, most folks find this a little bit more challenging than Project 1. So start early-ish. We are still in the hours before fall break is to begin. And if you have a little bit of time and want to keep your coding skills sharp over the break, then feel free to do so. It should be completable by those who start after the break as well, or at least log a few hours before by taking off for the long weekend. But a lot of folks in the past have gotten pinched, and that's even without a break necessarily getting in the way to cloud their minds. You've been warned in that respect. So let us take a look quickly at each of the problems there. In a moment, we'll download the code pack that's mentioned up here. But when you get it, there'll be several things to sort of observe. The 3 problems have 3 sets of different files that are associated with it. There are some BAT files, BAT Cave, BAT Orang, BAT Man, and then BAT files. These are actually short for battery, as the 2 T's would imply. And the embedded setting that you'll be working in has to do with a little battery sort of simulator that could be a real device, but we don't actually have one right now to test with, so we'll simulate that. Then the second set of files has to do with the problem 2 on this puzzle box business that's going to use the debugger. And then the tree stuff here, and primarily what's in the data directory, those things are inputs to this tree application that you develop over there. Note, as ever, the create this file, it's not going to be part of the code pack. It's instead the main implementation file for problem 1. Create these 2 for problem 3, and so on and so forth. A lot of things provided, but some of them you'll have to make for yourself. As was the case in the preceding project and the labs, there's a make file with handy commands like make test and make submit and so forth. And ultimately, you'll probably evaluate most of the correctness of your code based on some make test invocation, something along those lines. So starting with this first problem, which is an embedded problem, I'm going to bypass this sort of portion. It's worthy of reading for orientation, but we'll return to it in just a second as you get oriented. Basically, what you're going to do is this, and we'll return several times to the pictures over there. There's some battery, and it's plugged into a device, and on that device is a little CPU, and you're coding for that CPU. The main job of that device is to read some sensors that indicate how full is this battery, and then to create a display that gives a somewhat appealing human visual rendition of whether or not the battery is partway empty or entirely full over there. So eventually what you're going to do is construct this little LCD display. One of the primary factors involved in that is to manipulate bits, because each of these little panels here, for instance, this unlit panel that's numbered 10 right here, and this lit panel that's numbered 11 over here, they're controlled by an individual bit, and that's connected to a C global variable. The global variable, I think, is BAT display port. We can look at that in just a second. But this is oftentimes how embedded systems that you're coding against, little devices like watches or some little gadget like the little thing that I have that houses my microphones and so forth. There's some little CPU in there that's partly controlling what the device does, and then it's responsible for turning lights on and off via the fact that it can look at sensors and then execute code, placing certain bits at some spot which turns on lights that display in a certain pattern a 4 when it's on the screen. Now, when you look at this bit encoding up here, this is by no means 4. It's not the 2's complement rendering that you can do addition and subtraction with. Instead, it's an off light here, that's the 10, an on light here, because this bit is connected to this little panel over here. So when there's a high voltage, a 1 that's stored there, then this thing turns on. A 1 here, that's the 12, so we're going around a little or a clockwise circle here. 12, 13 is off, you can see a 0 there, 14 is off, 15 is on, that's right here, and then 16, that's the last middle one, that's on there. So that sequence of zeros and ones turns on and off certain lights that show a 4. And that's as simple as it gets in terms of like on light, off light there. But what's interesting is by putting this pattern down, you see a 4 by then. Likewise, there are some patterns that are sort of displayed over here in the high order bits of this integer variable. There are up to 32 ones and zeros in here. We only use up to 28 of them here. Some of them are tied not to these little panels here, but rather to the little panels that are here that are in the little sort of visual battery indicator. So there's a 1 in 24 and 25, so the first 2 bars are lit, indicating a certain sort of visual range that this number falls into. Now there's an alternate display here. This is shown in percent, so there's a little light on for that. But that can also be turned off if instead the battery meter is supposed to display things in voltages. And we'll make that connection in just a second. So the little V is on here. The dot is on as well, because now this is 4.23 volts here. And that indicates a completely full charge in the battery. So this thing's all the way up to the max there. Now there are several other examples here, and in a little while we'll put together some code that shows you don't have to write the code that displays this stuff. We've got a little ASCII simulator. Instead, you'll be responsible for reading sensors and then constructing this bit pattern over here in order to show, like, according to the sensor readings, the battery is almost empty over here, or it's got a little bit of charge left, as is the case in these other examples here. So we'll return to these examples like several times over as we look at that stuff. Now, to get oriented, you're only going to have to write 3 functions for this. They work with some global variables, and so we'll introduce those global variables to begin with here. So typically a little embedded device like this, a cheap way to check what the battery level is to measure the voltage that's coming off it. So you can attach little sensors to these to say, oh, there's some voltage level like 3.82 volts coming off this thing. And then hook that up to some part of the memory and then map that to like, oh, this is the C variable that we can call like bat voltage port. So that allows you to read a voltage level and then use some handy-dandy chart that some hardware engineers constructed to say 3.8 volts for a lithium-ion battery that goes into these little electronics, that's full. Versus if you were to see instead 3.4 volts, that's about 50% discharged, and when you get down to 3.0 volts, that's low enough charge on the battery that we need to actually just cut it and stop draining it. Because if we continue to try to draw current from it, it will damage the battery and you won't be able to recharge it later on. So most of them have little voltage detection circuits that are in there. But that means while it's in operation, you can actually look at this variable, which will have some number between 3.00 volts and 3.80 volts, do a little bit of conversion, and then figure out what's the voltage level and convert that ultimately to then a percent if you're so inclined. The voltage port is set up so that it has some reading of what that voltage level is, although it's not a direct reading of voltage. Rather, it's in units of 0.0005 volts. So that's a half millivolts. This would be decivolts and decavolts, and then I think millivolts, like 1/1000th of a volt. And then half of that, then that's what the unit is. So if you saw just a value of like, we'll go into conversions here. So a value of 6,000 for that sensor, then that would be 3.0 volts over there. And you want to show such things there. So there's a little bit of math involved, but the math is pretty easy. It's like, the sort of battery voltage, if you divide this sensor reading by 2, it gives you the sort of like, okay, in thousands, like how many volts are there? How many millivolts are there? And to boot, the scale of this thing over here is nice in that if you subtract off 1,000 from the voltage level you measure and divide by 8, oh, that's the percentage full it is, which is sort of by design to make it somewhat easier for all of us here. Now, those of you who are hip to the whole like, oh, there's that bit shifting thing, you might note that, oh, this is a power of 2 and this is a power of 2, and it's a good thing to note that you can affect those kinds of divisions with a right shift instead. And that's actually going to be a required part of the project, that you demonstrate some right shifting instead of division there. And it's also nice because later on, we'll recode this entire thing in assembly, and doing a right shift there is a lot easier than doing a division in instruction. All right, so first global variable that you have accessible in the C code that you'll write shows you how much voltage is on this thing. Do a little bit of conversion in order to get the actual voltage value, and a little bit of further conversion in order to get the percent full the battery is. The second global variable is the status port. It gives an indication largely of various things, but the one we're concerned about is, should I display things in a voltage format or in a percent format? And you see those are two options that are down here. In the one case, you show something like 49 and then the percent over here. But in the other case, show a 4 point something over here and a V over there. And so depending on whether or not a specific bit in that global variable, the bat status port is set, you do one or the other. And that happens to be the bit at index 4. If it's a 0 there, then that will be to show things in volts, otherwise to show things in percent. And so there's a couple different options. When you want to sort of read this thing, then you wouldn't want to read the whole value because there might be other bits set in it. You can't just do an if bat status port. Instead, you'll have to do a little bit of bit shifting and masking in order to determine this one specific bit, is it set or clear? Then I'll make a call on volts versus percentage there. That again harkens to things folks often have to do at a very low level like that, of inspect individual bits, which is accomplishable with those bitwise logic operations like bitwise and bitwise or, and with the shift operations. So you can use some combination thereof to interrogate this single bit there. Finally then, the last global variable that's at stake is the bat display port. Now this is the thing that's shown in the pictures here. That's a 32-bit integer. And it can be thought of potentially as an integer that you add and subtract 1 and 2 from, but it's better thought of as just a big giant array of bits, with the low 3 bits controlling some of the special lights like the voltage and the percent and the dot over here for the decimal point. Some of the middle bits here controlling different panels in the numeric display for the display panel. And then the uppermost bits that are over here, starting at 24, showing or hiding the little level meter here for the battery. So this is the one that will probably be of primary interest in the middle of the code that you're writing. Each of the bits controls some little LCD light that's on or off there to sort of render the display. And it'll be up to you to construct that bit pattern so that it shows appealing things, rather than a bar here and a bar here and a 3 here and nothing here and a negative sign there, and both these on at the same time. That's the kind of thing that will, sort of turn users off and, give them a sort of a reason to find something else to buy on Amazon if they can stomach it. So then, the functions that you'll write then that work with these are threefold. Ultimately, there's just a sort of update routine, but this is the last one to write. So we'll start instead with the set bat from ports. The documentation for this is just read this global voltage port, do some conversions, and then fill in the fields of this little bat struct right here according to what's the current voltage level, what's the current battery percentage, and should I just be displaying this in volts or percents. There's a struct definition for that down over here, and it's just dead simple. That you've got a field for how many millivolts is in the charge right now, what's the percent, and what's the mode. It's a tiny little struct with a short a character and a character, and you've got a pointer to it here. So you do a little bit of math after reading some of those global variables, and then you plop down appropriate values here in the struct. It's pretty easy. It involves a small amount of bit shifting, and we'll sort of get started on that as we sort of roam through the code in our initial foray here. There's a bunch of information here then about how to do some of those conversions. It's repeated of what's above there, so I won't belabor it here. This is not too bad, and you should be able to finish this up in fairly short order. Just be mindful of some of the constraints. that you'd want to avoid using the division operation, like the slash symbol in C, because that's an expensive operation, and the intent is for the update code that's in here, including this set bat from ports, to run many, many times per second. Usually these embedded processors are pretty underpowered, so you want to be sensitive performance on that. Avoiding the 30 clock cycle division instruction is a good way to do that, and also prove that you know how to use shifts in place of division when it's appropriate to do so. A few other constraints: make sure that you use integer operations only. There are some things that look like decimal points up here, but it should be apparent that all the global variables are integers. All the fields of this struct down here are integers. In fact, the target CPU for this thing isn't going to have a floating point unit, so you can't do fractional calculations with it. Rather, it's sufficient in this case to just do everything in integer land. And there might be a few remainders here or there that involve rounding up, but by careful use of masks and shifting, you can interrogate that stuff and just add one on to round up there. So don't use floating point operations. No floats, no doubles, no expectation of that stuff, because the processor will just not have the wiring to do that stuff, and so you shouldn't code against that expectation. And then the final constraint is, ultimately, we will take this entire problem in Project 3 and recode it in assembly. So the shorter and cleaner that you can make the code for this function, the easier time it will be converting it over to assembly later on. And so there's a sort of constraint that if you write something that's longer than 40 lines, that has deeply nested conditions and so forth, this will be a huge pain in the ass to convert to assembly. You'll both be hurting yourself in the future and also then losing some style points, because we'll peg you for that and recommend you get help from a TA to convert this to something a little bit more sane that will make your life easier as you're coding it in assembly there. So be aware of those constraints as you're starting to code on that thing. The second function is the most interesting and the one that folks have usually the most sort of difficulty with, so allot yourself time for it. Given one of these bat structs, as an actual struct as an argument there, fill in whatever this integer display is with a bit pattern that is supposed to look something like those pictures we were looking at. Something like this, where there's some ones and zeros here that turn on the percent sign, some ones and zeros here that put the 8 here, some ones and zeros here that put the 7, a blank here, and then the sort of little battery meter that goes up. Now, this is usually done by breaking things down to say, basically I've got 3 digits, a little meter that goes up, and then some special cases over here. So for instance, one might immediately realize in this case, I'm in percent mode. And so how would I know that? Well, the little bat thing that I'm getting here as an argument will have a certain value in the mode field here, a 1 for percent. And so that's the easy. It's like if there's 1 there, then I should plop down something at this bit position, at bit position 0, to display a percent in this case. And then you want to interrogate, which of these 2 fields should I look at, the millivolts or the percent? Well, obviously the percent. And say, there is an 8 there. And so somehow I have to know to get this little pattern, like here, at this position. That can be a bit daunting until you realize, like, oh, there's a method of the madness. If this was, 88%, I'd want the pattern of all ones here and also the pattern of all ones here. If this was 77%, I'd want this pattern of ones here in this positions 10 to 16 for this 7, but the exact same pattern shifted over a little ways to make this a 7 instead. And so wise coders will take the following approach. They'll look at what is the bit pattern for all of the digits, and a kindly professor has provided that to you in a little diagram over here. You need but just code this in some sort of fashion. As long as you know how to code binary constants, you could put this in like, oh, array index 0 has this bit pattern in it, and array index 1 has this bit pattern in it, and array index 2 has this bit pattern in it. So if I discover, oh, I need an 8, because that's the first digit of this thing, it's the rightmost one here, then you go into that array and so, oh, at position 8 in this array is this little bit pattern. Let me just shift that over, right here, 3 beyond, because that's where those special bits are at, and I'll just OR that on to the little percent thing that I had here, and voila, I've got an 8 and a percent sign. And then you look ahead and say the next digit that I see in this percent is a 7. And so I'll shift that yet further over and OR it on at this spot, and voila, you've got the 7, 8. You need but then go a little bit higher up and sort of figure out how many of these to put with maybe a sort of little conditional of like, if yay big, put this many, otherwise put this many, otherwise put this many, and so on and so forth there. So once you get your head around like, oh, I could put these patterns, not as numbers, but as bit patterns in an array where this is the pattern for the number 0. This is the pattern for the number 1. This is the 0th slot for the array, the 1th slot for the array, the 2th position in the array is this bit pattern. Then becomes an easy lookup, like do a few divisions by 10 to figure out what the digits of your percent or your millivolts are, and you can just fish out of this array of things the different bit patterns that you OR on. There is a somewhat more lengthy description of that here, but if you want a verbose version of it. But that's by far the most interesting and fun part of this, to sort of treat those patterns not as numbers themselves, but just as data that's stored in some array in the 1, 2, 3 slot, and then fish them out, scooch them over using some shifts, and OR them on to some growing sort of bit thing that's there. Finally, the overall update function is just called bat update. Its job is to call the other two functions. If it errors out, then you return a 1 to indicate something went wrong. And that will only happen if these other two functions like screw up somehow, like something goes haywire in them. Otherwise, it will update the display port, this global variable that shows, put a bunch of 1s and 0s in this thing to show the 1% that remains in the battery, the most common percentage that students come in with their laptop charged at to my office hours, by the way. And then, and then return a 0. So there's no need to really malloc anything here, so you might do a little bit of stack allocation, and that's fine. So before we get too much further, there is a little simulator for this thing that's handy to know about. And so rather than look at examples over here, I will actually go futz around with it a little bit to show you, because that's part of the code pack. Let's get the code pack and get started on that. I come back up here, right click on this thing to copy the link, and then zip over to my code editor. I think I've been mousing around too much here. Let's see, and then I need a terminal in here. I'll wget the P2 code pack, so that's present. I'll unzip the P2 code pack. It creates a folder, and I'll come in here and change into P2 code. Voila. Okay, so as you look around, you'll see we're missing the bat update.c file. That's the primary implementation file that you need. If you try to do something like make prob1, it'll just say, I can't find this bat update.c. You need to create it. So let us create it. There are a variety of ways to do that, but whatever your method of choice is for your editor to create a new file in here, go for it. And me, it's the esoteric Emacs invocation, Control-X, Control-F, maybe F one more time so I can name it. I'll call it bat update.c. We'll probably want the header here, and should you forget about the various things that are part of this, there's some mention of it here, the bat t struct, the 3 functions that you're to define, and then a mention of the variables here along with some documentation. Quick side note, this extern designation means there's some other implementation file where this global variable is actually present. This extern means the global variable will be around, it's just not in this header file here. It's very atypical to declare, actually define a global variable in this kind of context. If you poked around a little bit, you'd find that it's actually in the simulation thing, that here's where the short, the bat display port, and the character that is the bat status port are at. But I'll digress on that because the simulation file here, that's my business that I did. You're free to look at it, but you're not obligated at all to understand what's going on in there. Okay, so let's grab that header file. We will pound include as ever. And then we're supposed to have 3 functions in it. They were described over here in the problem room description. I could sort of copy and paste here. Actually, maybe I'll do that because I want these comments here. So the bat set bat from ports, plop that one down here. And then the set display from bat, that's here. And then finally the bat updates, the update function that takes no arguments and returns success or failure. Now again, none of these are implementations. They're instead just declarations that such functions will be provided. So if at this stage I try to do a make prob 1, then I get a different set of errors because I definitely got this file around. It will compile and be utterly empty. And later on I'll get linkers errors that say, hey, you said you would give me a bat update and these other things here. And in fact, those functions are not present. There's no definition for them. But as we've done before, you can quickly rectify that. This is supposed to return an int. Let's return 0. And then up here, this thing's supposed to return an int, return 0. And this one's supposed to return an int as well. I'll return 0. Voila, what lovely function definitions I can at least build. And you can actually, test now, though your expectations for how many you'd pass should be low at that point. But hey, running tests and failing them is much better than not being able to run them because your code won't compile. So in that respect, we're partway there. Then you'd want to start looking at these series of tests here. They indicate which function is being tested in each of them, and these are semi-proper like unit tests or function tests, however you want to call it. That there's some tests for the set bat from ports, the first function, some tests for set display from bat, the middle function, and then a few for bat update. And then finally, those are used in a main application that's provided to you. But if these functions don't work right, then the main application probably won't work right. So in that respect, like we just probably go in order. Set bat from ports for a 0 sensor value. Might look at the sort of test results right now, but probably more likely just read the documentation and try and figure out like what to return here. So for instance, if you were reading this voltage port here, you might wonder, like, well, how do I get access to that? Well, you can, in fact, just access it. It's a global name, bat voltage port like this. I could say my int x is this thing, and plop down a little debug printf x is now d. Of course, this output isn't expected, so this will automatically fail the test, but we'll be able to see it in the test results. Maybe over here, I'll just make test prob run test num equal 1. Now there. Oh, shoot, I should probably, there's no, no pound include of stdio here in the header file because it's not expected that you need it. So I'll do so here on my own just to make sure. Now we're good to go. And if I look through over here, you see the x is now 0 over there. And down over here, there's sort of nothing done right on this part. But generally, then you'd have to start looking at functionality to say, in this test case, the voltage port is set to 0. The bat status port is set to all zeros. So the 0 meant there show things in, I think, % mode. Or no, it's in voltage mode, sorry. And the bat display port started out as -1. We're not supposed to do anything with that. But what happens is like the struct that's being set that we're asked to please populate this with stuff here, it just has all zeros in it, and that doesn't match the expectation where if you're in voltage mode, you're supposed to put a 2 here. So here's a cheap, but ultimately, it'll fall down way to get this thing to work out all right. We can put here this bat arrow mode equals, let's see, I think there's a header file definition for this. Let's see. Oh, no, there isn't. Okay, so we'll just pop a 2 down there, and that'll be good enough. And probably get rid of this printf, and since I'm not using that's over there. And I make test prob 1. Still failing. Let's see. Oh, okay. So this is a multi-part test. Like the first segment was okay because I've got the 2 matched right there. The second part was less okay because the mode over here, like it didn't match up properly there. So in that respect, like, hey, like I can't always assign 1 there because sometimes it's supposed to be, or always assign a 2 there. Sometimes it's supposed to be 1, and sometimes it's supposed to be not 0. So you'll start looking at the global variables and figuring out what to put where through conversions and when to set this to 1 versus 2 and so forth. All right. I think I will digress on that point, but filling in the definitions then for the other of those functions, that's most of the battle associated with this one. Problem 1, no problem at all as long as you get acquainted with the bit shifting operations. Let us move ahead to problem 2, which has a distinctly different character. So this is a sort of puzzle exercise wherein I will give you a program. You can look at the source code if you want, but ultimately you'll run this with an input file, and if the program likes what it sees in terms of the inputs, it will award you points, but it's up to you to figure out what the input needs to be there. It's not at all obvious from the source code. Rather, the intent is you fire this thing up in GDB and look at the way that the code sort of executes in sequence in order to get a handle on what your inputs in this input file are supposed to be there. The input starts with your unique directory ID. So you enter your terpmail at terpmail.umd address, and then the first part of that is accepted and is used to generate a unique hash. So your answers will not be identical to your neighbor's answers in that regard. You'll need to understand how to fire this up in GDB. So if you need to, use this quick guide to GDB that's provided as part of the course curriculum. Lots of hints and tips there. Most of you have already been using this because you've had some lab exercises on it, and some of you employed it for Project 1. But there are brief reminders here. Typical SIPO is going to be like, oh, break at a certain phase after setting up the inputs file as the arguments to this, and then run, take some steps, print out some values, and then rerun after you change the values in there. We'll demonstrate that briefly here. So I'll make prob 2 here, and that will compile puzzle box here. Running it, you'll see here it requires an input file, a text file. The first token is your, well, I say internet ID, but should really be your terpmail address. And so if I catted out that input.txt that's here, you'd see your directory ID at terpmail. Well, we'll need to change that in a second because running it as is will just get you a rejection of that. So there's something wrong with the email address. It's like too long out there. So let me divide this up now. My input.txt, I will plop down my old student handle, cough0095. And then if I run this on the left-hand side here, you'll see like that it's accepted, but you don't really get any points at this point because the random numbers that are plopped down here, the 1, 2, 3, aren't sufficient in most cases to pass the first phase. So let's look at those phases just quickly. I'll look at it in my text editor. Here's puzzle box. There's been a commentary up top that you can largely ignore, just advice to make use of GDB on this, and that's where we'll turn shortly here. But most of this is coming out of like after setup in main. Phase 1 is run, and if that goes okay, phase 2 is run, and that goes okay, you get more points, and phase 3 is run, then you get more points and so forth. And so it's down here at the phases that you'll probably turn most of your attention. Some slightly obscure code with a potential to return and earn points or fail and sort of lose out on further points that could be earned later in this thing. Now there's an A and a B and a C here, and I'll just admit up front that these are going to come out of your input file. And they have to match a certain pattern here, where if I add some value based on your hash, mod 41, on to A, then the B and the C have to sort of relate to A and each other in the following fashion. The hash here is a rather large number, and I certainly can't do mod 41 in my head. I could, of course, use a little calculator and do that, but that defies the spirit of this. And rather, as things move ahead, things get a little bit more complicated here, and way more complicated here, and way, way more complicated as you keep moving ahead here, such that you'd have a hard time with just a calculator and a strong will getting this done. The point instead is use the debugger, because that's not exactly thoughtless, but certainly there's less need for strain at that point. You can set a breakpoint at this spot and say, what is A now? And so let's do that. I'm going to just adjust my editor so I'm over here. And also I need a terminal that's sort of normal rather than my Emacs terminal. Get over here into the project2 directory, and then invoke the gdb-2e on puzzle box. So this will get me source code. It needs an input file, so you can affect that by doing a setargs input.txt as such over here. Is it setarg or setargs? I can never remember. You can also run GDB from the command line with a certain invocation that'll get that effect, or just say run input.txt. Doesn't matter. And we'll probably also want a breakpoint here. So let's break at phase 0 and then tab complete. So there's a bunch of these, so phase 1 in that respect. So breakpoint there. And if I run at this stage, the screen gets a little mangled, mash Control L to redraw, and voila, we've got a breakpoint here at this thing. Over here on the right-hand side, I'm going to pull up that input.txt again. And it should then come as no surprise as I would next here, and next here, and next here, and next here, and then print out what is A. It's 1, because that's where it came from over here. Print out what is B, it's 2, and print out C, it's 3. But if I next one more time here to move ahead, I can now just ask, hey, what's A? It's 36. And so this should be enough information, along with just a hair of reasoning to understand for my input of A of 1, it became 36 by virtue of whatever my hash mod 41 adding onto it. And so I could try and change A, but I'm probably better off just leaving that and trying to change B and C here in order to match the pattern that's required here. A has to be less than B. So let me make this 40 instead, because 36, as it stands now, is definitely less than 40. B has to be bigger than C. Hey, that's good, because 40 is bigger than that. But A also has to be less than C. And so I'm going to take this one, and it's 36 here. Let me make this 38 instead. Now that's a change to the input file. Information from that file is already into the program memory. So at this stage, I'm destined to fail because, next, I should say, that I won't meet the conditions in here based on the previous contents of the file that were read in. But if I rerun at this stage, and then start nexting ahead here. Now, if I print out A, it's 36, but my new value for B is 40, and my new value for C that was reread in is 38. And so if I next now, I should fall into the case that I want, which is to bail out of this thing, not hit that failure, and come back up and earn some points. Now, there's no expectation that I get any more points now, so if I continue the debugging session, this will bail out, but hey, I've got 3 out of 30, and that's, 10% of the way there. And I then turn my attention to, let's break at phase 02. And then maybe rerun the program, finding that like, oh, I still have a breakpoint set here, so maybe I should disable that one. So I think that's all it's needed. Yeah. So I'll run again, and this time, this is, oh no, shoot, I disabled all of them, sorry. Enable the second breakpoint, now it's like back on over here, so you can toggle them on and off. So I'll run, and this time hit breakpoint 2 by bypassing breakpoint 1. And we'll start the whole rigmarole all over again. This was asking for 3 numbers and does slightly more complex things in order to get a relationship there. And I won't bore you by going through that. This one's still pretty easy. But they do get more difficult as you go ahead. If you look back over at the project spec, you'll find at the bottom of the description here some assertions about the kinds of puzzles that you're likely to see. You're going to see some kind of wonky syntax and so forth. There are up to 40 points available if you complete the entire thing, but 30 points is considered full credit. So anything you earn beyond that, and they're primarily earned by the last 2 phases, 9 and 10, those earn you makeup credit. So if you lost some credit on project 1 and want to earn some back, here is your chance to do so. Complete the entire thing. Just make sure you complete the rest of the project, otherwise if you get a 80 on this one, then those makeup points will just go to plugging the gap you had here. And if you end up getting 100 or more on project 1 and more on this, then hey, your pool is big, and so you've insulated yourself against problems later on projects 3 and 4 and 5 and so forth. So that's project 2. It is a debugging exercise, puzzle box. Have fun with it. Students generally report they're at least passively interested, and some just love puzzles, and so this might be your jam here. We will revisit this in the assembly context as well. Problem 1 dealt with coding in assembly, and you'll have, coding in something in C and that battery implementation, you'll recode that in assembly. Problem 2 deals with this puzzle box business, and you'll get an assembly version of this in the future, which will require you to use the debugger to figure out what kinds of inputs does this assembly level program require in order to earn points. The final problem that won't have to be translated to assembly is to implement a simple tree set. I think it's worthwhile just go through a demo. Once you complete this thing and run this little tree set main, you'll have a little main routine that's interactive. It can do certain things with the tree, like add things into it, figure out if a particular token is in there, find out what size the tree is, save it and restore it from files, and then print it out and so forth. So just briefly walking through the example over here, if you add a bunch of things in here, like Lucas and Mike and Dustin and Will and Elle, and then ask how many nodes are in the tree, it should say 5. And if you print it out, you get this slightly weird looking sort of rendition of what the tree looks like. Now, I'd encourage everyone to sort of, well, let's see, if, as you're trying to understand this, tilt your head to the left, and you'll see, oh, the first thing that was added in is Lucas. That's here the least indented. It's actually the root of the tree. And then if I were to insert Mike in a binary search tree, Mike sorts after to the right of Lucas. And if you tilt your heads to the left again, you'll see, oh, if this is the root, this is a right node of it. And if you add Dustin, that should go to the left of Lucas. That's over here to the left if you tilt your head but don't hurt your neck like doing such things. Like it's just sort of meant to be, this is the cheapest and easiest way we could get a printing that kind of reflects the structure of the tree, while still then giving an easy sort of time printing it. And this is a sort of reverse sort of pre-order or post-order, reverse post-order, I think, something along those lines. Now, there are other orders of trees that you might print out. In particular, if you study these things, and hopefully you have in a past CS course like CMSC132, then you know there's also such a thing as a pre-order traversal of the tree that would start with the roots and then visits all of the left parts to the roots, and then later on visit all to the right parts of the roots. It's a recursive sort of visitation of that tree, just as the reverse pre-order is, or post-order. But then on arriving at the node Dustin to the left of the root, you print that out and then go to all the left parts and all the right parts, and then eventually work your way back up to Lucas and go to its right parts, all the left parts, and then all the right parts, and so forth there. So this output over here is commentary on this and isn't necessarily like part of the output that you have to do. Rather, this stuff is like associated with just commentary on the structure of the tree and how it would look then as printed in these two representations. That means you actually have to effectively build the tree, have some kind of function that adds in and so forth. But the primary purpose of such trees is not printing, is to figure out with relative quickness whether something is in or not. So figure out if Mike sorts to the right of Lucas, and so we'll look that direction and voila, we found Mike. Nancy, if she's in there, should sort to the right of Lucas. Nancy's not Lucas, so go to the right of that. Mike is not Nancy, go to the right of that. Go find Will, that's also not Nancy, go to the left of Will, but we're at a tree at this point, so Nancy cannot be found in the tree. So let's add her, and then ask, like, where does she go? Well, that would be add her to the right of Lucas, to the right of Mike, to the left of Will, and that's where Nancy should go, because you found a leaf at that point. So, like most set implementations, the tree set will avoid adding duplicate elements. So as the addition happens, or before it happens, you check whether or not Mike is already in the tree. It is, so the duplicate element is ignored, as it is for L over here. Adding things in then should sort of adjust the structure of the tree. Hopefully this is not new information to any of you, but that you can do some traversals, you can do some adding and so forth. We'll look at the functions to do this stuff in just a moment. What might be new is saving and restoring such data structures. So part of the functionality in this little routine, this main function, is to be able to take the current tree, write it to a file on disk, and then clear out the entire tree so it has nothing in there, and then load it back up, this past version, which will replace the current tree with whatever is read off a disk. That's super easy if you store on file or on disk a representation of the tree in its pre-order, so that if you said, hey, Lucas is the first thing that's in the tree, it's the root, so let me put that first in the file, and then after that put Dustin in the file because that's going to go to the left, and maybe L because that's the left of that, and Mike, and then Will, and so forth. Those things then are great because the pre-order rendition allows you to just add these things back into a tree and you get the restoration of that tree there. So that's essentially how the file saving and restoring is going to use. Output a pre-order traversal, and then when you're loading something, read that pre-order traversal and just add the nodes in order. More information on that appears later, but we'll get there when we get there. All right, so there's more to this demo if you like, but this is actually one of the test cases, so it's not a bad idea to study to make sure that you're on board with it. The tree itself is to have a defined structure that has the following structs in it. There's a struct for the tree itself, which is basically a root and a count of how many nodes are in it, so we don't have to count all of them on the fly to figure out how many are in there. And then a node structure that has a left and a right branch along with a bit of data, in this case character data over there. This shouldn't feel particularly foreign to you because it's almost exactly like the linked list that we dealt with, save a change of names for T nodes or TS nodes and tree sets, and the fact that instead of one next, there are actually a couple next in tree nodes, so you can go left or right instead of just straight on to the next linked list node. There's some description of standard options here, and then a more or less required set of functions that you should implement as part of this. So this main function here that you'll eventually write as well, it has a structure where, oh, when I want to add something, I call an add function. And in order to get that add function right, you may write some additional helper functions, but at the sort of least you need this tree set insert to be present there, along with here's the tree I'm inserting to and the new thing that I'm adding in there. This should use the most efficient way we know how to update trees, an iterative approach or loopy approach if you like. So shy away from recursion in this case. There'll be other spots in here to use recursion, like removing everything and printing in certain orders, like the reverse post-order traversal and the pre-order traversal. Those necessarily have to be recursive, so that's fine. But this is essentially the outline of the minimal required functions that are needed. The only other thing then is that's required is a main that exercises each of these and does some stuff. Now that seems like it might be kind of daunting to set up, but have no worries. As we've done before, you can just grab this thing here, do a little copy, jump back over to your code. We're done with this inputs.txt. So come back over here, and I'll make myself a new file, the tree funcs.c. Plop this thing down, and then proceed with that somewhat pedantic exercise of replacing these with, return or nothing at all. Or in this case, it's an int, so I'll return 0, and so forth. So I'm not going to bother doing that for the remainder of those because it'd get boring. That will put you in the position to compile part of what's required for the third problem. So I'll make problem 3. But we have no treeset main.c yet, and so we shall have to make one. There are smart and dumb ways of going about doing this. A dumb way would be like, okay, I'll create a main, and sort of zip through and start filling things in and try to remember how to re-input and stuff like that. A somewhat smarter way to do this is to call upon your experiences and try and remember, I feel like I've done something like this before. Maybe even in this class. Let me think about this just a little second, and after you do, and perhaps peruse past materials, you might discover the fact that this is a lot like Lab 2, where you were tasked to finish an implementation of a list main and a list funcs, and a lot of the infrastructure there was provided for you. And so it's maybe not a bad idea to lift some of the code that was associated with that. If you've lost that code, like shame on you. Why are you losing code in today's day and age with all the possible backups you have? Get yourself a Dropbox or a Google Drive or a OneDrive or whatever the hell Apple is using, but back up your code for God's sakes. But if you did, you can sort of resort to other measures, like jumping over here to Lab 02 and finding I can re-download the code pack. It's not complete in this case, but I don't need it to be complete. I just need the scaffolding and infrastructure that's provided there. In particular, this list main is going to be useful because I can rename it tree name and benefit from the fact that a lot of the structure is already set up there. So let me grab this thing because I don't know that I have it in this directory, and it's a good practice for it. Zip back over here, I'll change up. Looks like I don't have Lab 2 code, so I'm going to change my terminal in there, do a wget on Lab 02 code, unzip Lab 02 code.zip, and I've got it now. If you already had one around, please don't re-download it. You might overwrite your hard-won solutions to that stuff. But this will be good enough here so that, well, I can actually use some Unix magic for this. Let's take this list main.c, copy it, it's in Lab 02, list main.c, and I'm going to copy it to a different destination. This is now p2 code, and I'm going to call it tree main.c over there. Now that's the Unix copy command, source file, destination file. They can be buried in folders someplace if you want, but this is good enough for it. If I zip back over to project 2 and refresh, I now have a tree main.c, which is ironically got a lot of list stuff in it, but that's more or less expected. Maybe I'll change my comment. It's like, now it's a tree main. Ha, ha. Etc. And so then we'll start making some changes, like this will be the treeset.h, or wait, no, is it tree main or treeset main? Crap, I think I copied this wrong. Okay, let's sort that part out. Make prob 3, there's no treeset main. Okay, so I even copied the name wrong. Let's rename this file. Move the tree main to tree set main.c, and then I'll have to probably refresh this thing. Okay, we're back in business now. And then there'll be a bunch of things in here like this linked list demo business. That's no good anymore. I'm going to poke around and hope that maybe Kaufman provided something like what I'm supposed to do. And oh my God, what a nice guy. I don't even have to type all that stuff in. I could just copy and paste the help message that he provided because he was sick of students typing in wrong and complaining because they failed test cases there. But this part is like exactly right now. And then over here, I'd want to start making changes like I'll probably want a tree init of some kind, and maybe instead of a list t, tree t variable and call it a tree, something along those lines. Maybe change comments for this over here. And then at least I can get the prompt right. It's supposed to be this ts and then hash and then forward. So ts short for tree set and a hash there, something along those lines. And yeah, maybe that's enough for now. I'm actually just going to take the rest of this stuff, come all the way down here because I'm lazy, and comment it. Now that's where that block commenting is super candy. Maybe I want to save some of this because it's kind of close. So, I could maybe get the, is it exit or is it's quit, because Kaufman actually wants me to change a few things in here. So I'll maybe uncomment that one and then echo it back here. And let's see, now we might be able to build prob 3. Not quite there. Oh, there's a list clear down here. Let's just get rid of that for now. And then tree init. I don't know if do I have, I don't know. Time t? Oh no, okay. Let's see. I'm confused a little bit because this says tree t. Oh, because I didn't that. I got the wrong type name, didn't I? It's treeset.h. It is treeset_t. Okay, cool. Nice try, GCC. You're trying to say, did you mean time t? That's the closest thing I could find. But I actually meant treeset here. Cool. How are we doing now? No tree init. yet. Initialize memory, it's an implicit declaration. Boy, in my funcs, do I have one of those yet? Come over here. My tree. Oh, is it? I have the wrong file name too, don't I? Here, tree set funcs. Because I feel like I had. Yeah. Okay, so it is there. All right, good. Okay. So I'm gonna make clean because I'm a little nervous now about all the .os that are sitting around. And I'll make prob3, still no, okay, what is it actually called? It's tree set in it, not tree, okay. So there we go, set in it. Get your names right. All you IDE users probably had that straight out of the gate, but hey, we got there eventually, and it taught us to read compiler messages and see that they've gotten slightly more modern and actually give reasonable suggestions in some cases. Okay, so project builds now for problem 3. I can do a make test prob 3. Again, no real expectation that anything's going to pass right now. But it might even actually be worth my while to sort of look at, okay, this first test result, like what do you want from me here? And I'm actually pretty close. Like I just need to do nothing for the print command and actually implement some version of that in main. In short order, you could probably do that by coming down here and seeing, is there an existing print command anywhere? Oh, there is. Okay, so here I can just recognize it. I'm not going to do anything on that. I'm just going to sort of do the echoing, as it were, because I don't have a tree set print implemented yet. But if I make test and then work on that test num1, voila, one test in the bag. But of course, it's the easiest test. That's all I ever do in these videos, but no matter. You should thank me nonetheless, because I just spoon-fed you 1 point. All right, I think that's enough for now, and should be enough to sort of get you acquainted with, here's quick setup for each of those 3 problems, as well as some details about how you'd want to go about your business of completing them. Have fun with this one. It's a slightly bigger set of exercises to do, but each of them is distinct and brings its own little flavor to the business, and will give you some skills that sort of vary somewhat. Bit shifting for the first problem, debugging for the second problem, and data structure implementation, along with a revisitation of an interactive program for the third problem. That's all I've got for now. If I don't see you again before fall break, enjoy your break. Just make sure to get a bit of coding in. Happy hacking until next week.